Okay, so today we're going to do a lesson, a group lesson on magnetism. We're actually going to talk about one of the other fundamental forces that really make up what's known as the electromagnetic force. Um, we're very much into the section. Guys, we're very much into the section now of physics where we don't use a whole lot of formulas. We use very, very few. If I can do a quick recap of what we've covered so far in the electrostatics before I get into magnetics, there's really only a few formulas you need to have. Most of this is all concept. Okay. Here's a few formulas that you're hopefully getting yourself familiarized with. One is this one here. The amount of electrostatic force can be calculated by K Q1 Q2 over R squared. Okay. Close the door. Come on in. Okay. Someone actually had just asked in one of the reflections I asked you to do whether there's a difference between R and D. There is no difference. I may as well point that out right now. If you ever see a formula with D squared on the bottom, distance and radius really refers to the same thing. Let me see whether I can try to explain why they get used interchangeably if I haven't done that before. Let's say that you have a charge, just a point charge, like a single positive charge, and you want to figure out how much force there is between this positive charge right here, I'll call this number 1, and the negative charge that's over here. Ultimately, you need to know how far apart away they are. Okay. But let's say you took this negative charge right here and you moved it over here to this location right there. Let's say that the amount of distance that you had in both cases was, say, 5 centimeters. It's in a new location, right? But does the force amount really change all that much? I mean, I know it's in a new location, but the distance from the source, if I call this a source right here, the distance really hasn't changed. And so in a way, I can almost draw kind of like a circle. And any location along this circle has that same distance. Right here, put that same negative charge right here. That distance, it's still 5 centimeters. So sometimes you see it written as a distance, or if you can kind of visualize this, sometimes we call it a radius because we pretend that this is at the center of a circle and anywhere along this circumference would have the same value. I don't really care whether it's on the left or on the right or up or down. Okay, so hopefully that kind of answers any questions as to why you get distance or radius interchangeably, but that's one formula you should know. Okay. Second formula. We then discovered that you can actually count the amount of force if you divide by the charge, and you got to be really careful about what charge particle you use here, but you can then calculate what's known as a field strength. And a side note on this one here, the field strength, you definitely want to write the little arrow vector hat on top of it, because if you don't, it's energy. And I wish we could pick different letters, E for energy and not E for field strength, but it's a really common mistake. Make sure you put the little E on top. That's another formula. Another formula to find a field strength is you take K times by Q and divide by R squared. Now, both of these formulas are very similar, but the Q in each case is slightly different. One is the Q of the thing that's providing the field, which is this one right here, and the other is the Q of the object caught in the field. Make sure you are clear that these charges right here are different from each other. We also would have learned about a formula that you can calculate a field another way. You can make it V over D, V being voltage, and D being distance. Okay. Now, voltage and distance of what? This only happens in one very specific instant, where you have two plates. One is perhaps the positive plate, and one is the negative plate. And there is a field inside those two plates right there. Fields always point towards the negatives, right? Because they're what positives would hypothetically do. So there's a field inside here. It doesn't matter whether the object is here, or here, or here, or here. The field is always the same. The distance in this formula is not how far the object is away from the plates. It's how far the plates are away from each other. The further away these two plates are from each other, the lower the field. So if I maybe could, whether I can like select this. Yeah. See, if I move those plates further apart, see if I separated the plates there, that means the distance between plate 1 and plate 2 is different. Well, the field wouldn't be as strong because these two things are further apart. But I don't care where the particles are. These particles can be really close or be really far or right in the middle. That does not affect the field. So that's a fourth formula. Another formula that we would have learned is this one here. Energy is equal to voltage divided by... No, what am I missing here? Backwards. Let me try that one again. Oh, I want an eraser here. Eraser. Okay. Voltage is equal to energy divided by charge. And in this case, see how I've written the E with a little hat on top of it for vectors? This is good old-fashioned energy. Chances are it's kinetic energy, and you'll probably be making it equal to 1/2 mv squared. That's another formula we can use. There's one more formula that we're not really going to use a whole lot yet, but we may as well discuss it. Voltage is energy per charge, and current is charge per time. That's another formula you may come across. And that's more or less it. I don't think I've missed anything, but those are more or less our formulas that we use so far in the electrostatics unit. One of the interesting things is that you can link many of them together. You can make this voltage right here be equal to that voltage there. You can make this electric field be, say, equal to this electric field or this electric field. If you then know this electric field, maybe this force could be equal to mass times acceleration. Do you kind of see how you could link a whole bunch of these together in a chain of equations? Okay, that being said, formulas are not all we do in physics. Okay, I really need you to know less than 40% of your diploma involves math calculations. Most of what you need to understand is the theory and the understanding as to what's causing, like what is the reason why things are moving. And that's my segue then into our second half of the unit. Okay. All of these things that we were just discussing here are part of forces that we call action at a distance. You guys remember that terminology, action at a distance? Here, I am going to literally move my calculator with a force. But I think everybody understands why it moves, because I literally moved it. That's called the contact force. Action at a distance forces are forces where there's literally nothing between the two objects, and yet they still move. Right? Ancient magicians were able to be pretty good con artists. They would use electricity, they would use magnets, and they would be able to make a good magic show out of it. So this is the second half of our lesson then. The other action at a distance force is magnetism. So anyways, I'll do something I rarely do. I'm actually just going to read right off my slide here to start this one here. According to legend, the history of magnetism begins in ancient Greek around the year 800 BC with a shepherd named Magnus. Magnus discovered a rock was stuck to the nails in his shoe and staff. I don't really see this being any different than, remember when I had my magic wand and I had it pick up little pieces of paper? Right? He discovers that, hey, there's a rock stuck to my shoe. It's not coming off, right? Can you imagine someone being in that scenario and being like, that's really weird, that's cool, right? Now, that's the first, at least what I've found for research, that's the first recorded knowledge of someone kind of discovering this kind of concept. I'm sure it was discovered well before 800 BC, but this is at least the first time we have it kind of recorded, if that's fair. So, what we believe now is that it probably was an iron ore rock that Magnus had discovered, and it was probably Fe3O4. I actually want to pause on that for a second, because for any of you who have taken chemistry, that may seem like a very odd compound if you haven't heard of it before. Fe3O4. You guys have all taken a little bit of chemistry back in grade 10, right? If you were to look at these charges right here, the only logical possibility for this is that oxygen would have to have, a -3 charge, and iron would have to have a 4 charge. That's kind of how that would work. But if you know much about the periodic table, oxygen has a -2 charge, and iron is either 2 or 3. So if this formula kind of perplexes you, I'm not surprised. It's actually, this is why I want to kind of mention it, Fe3O4 is actually a mix of FeO, which is called iron 2 oxide, and Fe2O3, which is called iron 3 oxide. And putting it together, you have 1 iron plus 2 more makes 3, and 1 oxygen plus 3 more makes 4. It's actually a hybrid. You actually get some iron 2 oxide and some iron 3 oxide in the same compound, which, I don't know. Anyways, I thought that was an interesting side note for those of you who know some chemistry. It is one of the magnetic rocks or magnetic materials that we know of. There are certain things that are excellent magnets, and so this iron ore is actually one of them. And like I said before, for a long time, magnets were thought to be magical, right? Because you could get things to stick together that you wouldn't expect. Eventually, someone really smart discovered this, and this is ultimately the fundamental thing behind why magnets are so important to us on Earth. It was discovered that if you put a little sliver of a magnetic rock on water, it would always spin and point north. And that fundamentally changed our world. Because once you made a compass, you could be anywhere, and you could have a way of tracking and find your way home, so to speak. Right? I mean, think back, before GPS, right? Before you even had like a map, right? If you were in a location that you weren't familiar with, how would you keep yourself safe and how would you get back home? Okay, one method would be like the drop breadcrumbs behind you method, right? So I start wandering in the forest this way, I drop some stuff behind me, I follow it back home, right? If you're not familiar with the terrain, right? But, I mean, another possibility is you wait till it gets dark out. Why would you have to wait till it gets dark out? Stars, right? And the stars are something that you can orientate yourself with, right? Well, as soon as someone discovered how to make a compass, now we have a way of always pointing north, right? So imagine you get lost in the forest and you just have no idea which way north, south, east, or west is, right? Oh, there's a third way you can use, by the way, the sun, right? You could look up at the sun, and if the sun is, setting over there, now you know it's west, now you know, right? But if you have a compass, that really helps your ability to navigate. Right? Boats used to navigate based off of stars at night. Well, now they have a compass, right? Anyways, so they discovered that you could put a little sliver on water, and it spun to point north as a compass. And so now we use this terminology. This is a word you're probably familiar with. It's called the poles, and they're the two sides of a magnet. And we've now since designated those sides of the magnet north or south. I want to speak to that for a second. We didn't have to call the sides of a magnet north or south. We could have called them A and B, cats and dogs, positive and negative. It really doesn't matter what we call them, but convention was dictated because of north and south. Okay? North, south, east, and west have been around for a long time, right? And so once someone realized that a compass needle always pointed that way, since that way was north, they decided to call it the north end of a magnet. Does that make sense? But they don't have to be called north and south. They could have been called A and B for all we really care, but that's how we designated them. Side note, north and south have absolutely no relation with positive and negative. Okay? There's no correlation between a north pole being positive and a south pole being negative. Just be aware that there are two opposites of each other. Okay? Which leads me to my next slide here, wherever it is here. Nope, I'm going to skip a slide. Now we have three different ways of talking about fields. We can talk about magnetic fields, gravitational fields, and electric fields, all three of which are action at a distance sort of things, where something occurs without direct contact. Okay? One of the things I want to point out is that in gravitational fields, no, I don't have the note that I want on here. Can I come back to this slide? Hang on, let me come back to this one in a second. Let me go back to my thought that I had right here. When you have magnets, magnets are north and south. Right? Electrostatics, positive and negative. But when you're talking about gravity, it's just mass 1 and mass 2. Right? North and south, they have opposites of each other, right? There's an opposite for electrostatics for positive and negative. But when you're talking about gravity, there's really no opposite of mass 1. There's just mass 2. Okay? One of the things that you're very likely to be assessed on theory-wise is some of the similarities and differences between the fields, and that's what I want to point out. But just be aware that there is no correlation between north and positive and south and negative. Is that clear? Okay, let me go to the slide that I was going to go to here. Okay, so we call it a pole. A pole points north, obviously, because it's based on the North Pole and South Pole. And it's got a similar thing. North poles attract other north poles and repel south poles, right? So just like a positive and a positive want to repel each other, a north and a north want to repel each other, right? So in the same way, there's a field. And this is a good visual demonstration of a field. We're actually going to do this in a second. Oh, we got questions, yeah. You are right. I definitely have that wrong, don't I? Thank you. I think I demonstrated it right here, but the words are definitely wrong, aren't they? North poles will repel other north poles, but attract. Thank you. Was that what you were going to point out too? Yeah, cool. Okay, I'm glad you guys are reading. You get the concept though, right? North and north repel, north and south attract. Okay. Here's a good picture of a magnetic field, and we're going to do a lab tomorrow, and I'm actually going to have you try to visualize a magnetic field. What is a field? Is there something actually there? No. No, a field is best described as a region of influence. A field is basically describing what would happen if you put something there. This is actually a diagram of what you end up doing is you put a bar magnet underneath, usually a sheet of paper. And then what you do is you sprinkle little pieces of metal on it. We're going to use the little iron filings. And what you'll discover is that as you sprinkle the metal on top of the sheet of paper and the bar magnet, that you start to see these lines start to show up. Well, those lines are basically what we would like to envision field lines to be, right? Where things are trying to point towards the North Pole, trying to point towards the South Pole. There's like lines between them. This is honestly no different than if you had a positive and a negative pole, and you started to draw lines that looked kind of like this between the positives and the negatives. You guys remember doing field lines like this with positives and negatives? They go away from positive and towards negative. There's a huge similarity between that and magnets. I doubt this will ever come up, but just for your own knowledge, there's only a certain number of metals that are actually magnetic. Most metals are actually not. Like, for example, aluminum's not really magnetic. But iron is, like we mentioned before. Cobalt, nickel, and gadolinium are the best ones. And the word we give is we give the word ferromagnetic. Okay. I think ferromagnetic is probably a poor choice of word, because if you know the word ferro is the prefix in Latin for like what we use for iron. You know the symbol iron is Fe? That's the Fe in the word ferrous. And so I think the word came about because iron is probably the most common magnetic material, but it's not the only one. No. So iron, cobalt, nickel, and gadolinium are the most common magnetic materials. Okay, here's the slide I wanted to discuss. The theory then between how all three of these types of fields are very similar to each other, but they're not the same. They all have some things in common, some things that are not in common. A couple years ago, every diploma had one of these kind of questions. You guys ever seen Venn diagrams where you have two circles and then there's like the overlap between the two of them? Well, for a while, they were always trying to put on a 3-circle Venn diagram circle, where this would be an electric field, this would be a gravitational field. I haven't shown you the formula for magnetic yet, so I'll just leave it as magnetic. And they were asking students to try to figure out what do electric and gravitational fields have in common, but not with magnetic, or what do all three have in common. So I really want to make sure you guys know the theory behind this, so I'll just read through some of the stuff on here. First one is that magnetic fields are very similar, but here's the big change. You can separate charges. It is possible to separate a positive from a negative. It is impossible to separate a north and a south pole on the same magnet. Okay, I'm not talking about two separate magnets. I'm not saying here's a north pole and a south pole right here, and here is a south pole and a north pole right here. I'm not saying that you can't separate those. You can. But you cannot cut that in half. Well, you can. But you know what it just makes? More magnets. You break a north-south magnet in half, and what ends up happening is you get a second south-north and a second south-north. You just make 2 more magnets. You guys know those like worms that when you like cut them in half, like it doesn't kill the worm, it just makes 2 worms? You ever heard of those ones before? These magnets are like that. So that is a really important thing here. Magnetic poles must always come in pairs. You cannot physically separate them. Scientists are actually trying to work on this. The name for it is called a monopole. And a monopole would be where you literally just have a north pole, no south pole. Because, I mean, can you have a single negative charge? Sure, that's an electron. Can you have a single positive charge? Sure, that's a proton. Can you have just a north pole? Nope, it's attached to a south pole somewhere. I guarantee it. One day we may discover that monopoles are possible, and I guarantee you it's winning the Nobel Prize for physics the year it's discovered. But it may not be possible. No, it may be physically impossible. So, okay, let's go through some other things that are the same here. Magnetics and electrics are similar because they're both very strong. Gravity is actually very weak. I don't know whether I've spoken to you guys as a group about this, but gravity is the force that we notice the most. If I were to let go of this eraser right here, I can see gravity make it fall. But it's actually a very weak field. The only reason we notice gravity is because the Earth is just so darn huge, right? Imagine that I have 2 magnets sitting right here. These 2 magnets will probably want to attract each other, right? But they're only attracting each other just because of magnetic field. Take 2 objects of roughly the same mass and put them close together. Is gravity making these 2 things be attracted to each other? Well, yeah, but is it a whole lot? No. Okay, so I know that magnets seem weak compared to gravity, but we only notice gravity because Earth is massive. There is very little gravitational attraction between me and the person next to me. Right? So anyways, electrostatics and magnets, very strong. Gravity is actually quite weak. There's a similarity between gravitational electric fields. They both have the inverse square relationship. If I haven't pointed that out before, the inverse square relationship is how the force is equal to 1 over the distance squared. The further away you get, you square the amount of force you have. Other similarities, magnetic fields and electric fields can both attract and repel, but gravity can only attract. Why can't gravity repel? There's not an opposite. There's not a doppelganger. There's not a positive to a negative, a north to a south. In gravity, you just have mass and other mass. Does that make sense? There is a direct relationship in all three of them, though. All three of these things have a direct relationship. It just depends on what you're talking about. The amount of field strength you have is based on your magnet, or the mass, or your charge. If you have a stronger magnet, you have a stronger field. If you have a bigger mass, you have a bigger field, right? So, and then here's the last one. We kind of talked about it. The masses can separate. The charges can separate. But can you separate individual poles from each other? No. And again, I'm not talking about two different magnets. I'm talking about cutting a magnet in half. You can't just rip off a south pole. So, pretty good on that. Highly likely you'll be assessed on similarities and differences between fields. It's one of the theory concepts that comes up. So. Okay, moving on from magnets. Magnets have a whole bunch of different cool shapes to them, depending on how you build a magnet or like how you're able to forge them, so to speak. Here's the three most common. I have some of all three. We're going to do a lab on this tomorrow where we kind of play around with magnets. One is a typical bar magnet, and usually the way a bar magnet works is that one side is north, one side is south. Pretty straightforward. This is a U-shaped magnet, and these ones are quite useful because they provide a lot of field between these two parts of the U, because this side here is north and that side is south. And it means that this little region right here is there's a strong field in there. Does that make sense? As opposed to this bar magnet here, which is kind of got a field that just kind of goes here, there, and everywhere. A button magnet, the way it works is the top side of the button is north, and the bottom side is south, if you kind of get how I'm drawing that. So a button magnet like one of these guys right here, this side could be north, the bottom would be south. Okay, let's talk about magnetic fields then. Here's the convention. Nope, not yet. Where's my convention for magnetic fields? Okay, we'll get to that in a second, apparently. Okay, this slide right here just talks about what I mentioned already. Monopoles are predicted by some people, but no one's ever been able to, at least as of the last time I looked it up. So, okay, now why? Why are monopoles not possible? Here's one of the theories as to why. It's called a domain theory, and I'll try to describe it with some of these pictures here. Okay, this right here would be what we would consider to be an unmagnetized object. And what's happening is all of the different, like, smaller little chunks, whatever they are, whether they're atoms, whether they're like small subgrouping of atoms, but if you can just imagine this little thing right here, one of these things right here, we would call it a domain. Okay? And each of these little domains, sometimes they line up nicely, sometimes they don't line up nicely. And so if it's just kind of scattered, this would be considered unmagnetized. But what ends up happening is if something becomes magnetized, everything points in the same direction. So then you'd ask the question, well, Chris, what is the everything? I don't have an answer to that, though, right? Because, like, what is a magnetic field? There's not actually something there that we can test. We can see the results of what it does. But you get what I'm saying here? Is that, like, there's not actually something tangible that we can go and look at here because we're talking about something very theoretical. But the theory, though, theoretical, is that whatever the heck is going on in here, whether they're electrons, whether they're nuclei, we're not really sure, but it's probably some combination of electrons or nucleus. If they are aligned all in the same row, it makes something magnetic. If they're kind of all aligned in opposite random mismatch directions, then they're not. This explains why a monopole isn't possible, though. I think I have a picture right here that helps. Here's an unmagnetized piece of metal, which has all these little domains that are basically little north-south magnets inside, and they're all just going in opposite directions. Here's something that's magnetized. Everything is all in a row, so whatever this little chunk is, it's lined up nicely with this one. What would happen if you cut this thing in half? Well, see how this side over here used to be north, and this side over here used to be south? If you cut it in half, but this magnet is really made up of like smaller little bitty magnets, those domains there, well then, see how south was the last thing we had on this side right here? This side would become south. And since I cut it in half right here again, see how since north was the last thing we had right here, it would make that north. So, I mean, it's not a great theory because how do you test this sort of stuff? How do you hop on a magic school bus, zip down to size, and look at something? There's nothing to look at, right? So, but anyways, that's the concept, is these little domains right here. If they align, that's what makes something magnetic, right? So anyways, electrons are kind of the key to what we think about, but we haven't even discussed the problem with looking for electrons yet. That's in our next unit. If you haven't heard this before, though, electrons are notoriously hard to find in the quantum model. It's actually impossible to locate an electron. As soon as you find it, it's no longer in the place you thought you found it. You know what? Actually, let's talk about that. This is a cool concept. I'm going to pause for a second. Just sit down for this one. How do I know that you exist? How do I know that you exist? This is deeply philosophical. Maybe. Okay, well, here's how my brain knows that you exist. Light is bouncing off of you. It's reflecting off of you, bouncing to my eyes. My eyes have receptors in there that allow my brain to basically make an image. How do I hear you? Well, you emit sound that comes towards me as well, right? Well, let's talk about what happens when you try to find an electron. If you try to look for an electron, light would have to bounce off of the electron and then bounce towards whatever it is that's trying to sense that electron. Here's the problem. Electrons are so small that when light hits them, they move. Okay? When light bounces off of all of you so that I can see you, light particles, we'll talk about photons eventually, but photons of light bounce off of you, reflect off of you, and bounce towards my eye, I can see you. You are large enough in size that light does not cause you to move all that much. But let's say you are the size of a little bitty electron. Light bounces off the electron, bounces towards whatever our sensor is, but now the electron is over here because it just got hit by something. Does that make sense? It makes it very, very challenging for us to do experiments on the smallest quantum level, because as soon as you try to find something, where you think it isn't anymore by definition. You cannot know where something is. You can know where it was, maybe you can know where it's heading, but if you were to ask me, Chris, where's the electron right now? We have no clue whatsoever. Right? Anyways, can you see why that would make it really challenging to talk about magnets? Because when we're trying to figure out electrons that are spinning, first of all, how do you measure a spinning electron? As soon as you try to measure the spinning electron, it's no longer where it was, because the mere act of measuring it causes it to move. So, anyways, I got a little off topic here because that's actually our next unit, but it kind of fits, so I thought I'd talk about it. Okay, I need to get back on track because I'm getting off topic here. Does anyone have any questions so far, by the way? Okay, so let's say that those domains then, however it is that they work, they manage to get locked into place. So you have a north-south magnet here, a north one here, a north one here. All these little bitty domains all are locked into place. So this little internal magnet, they all get locked into one spot, meaning this side is north and that side is south. It's a permanent magnet. Permanent magnets are pretty valuable because we can use them all the time. But it's actually possible to move domains around, and we can make temporary magnets. And what's cool about these is that these you can switch on or off. We have a name for these. Maybe you know this word. Has ever heard of an electromagnet? An electromagnet is very powerful, not only because you can really increase its strength and make it a really strong magnet, but you can just all of a sudden flip a switch and all of a sudden it's not a magnet anymore. The classic example is you go to a junkyard and there's like the big magnet that comes down and attaches to the top of a car, right? And then the magnet lifts up the car on a big crane, you drop it over here, and now you want to get the car off of the magnet, well, you just turn a switch and the car falls. You get what I'm talking about there? One of those kind of things. So, okay, other little notes about magnets. You can actually demagnetize them, because again, the whole point of a magnet is causing all of these little bitty pieces to align up properly, whatever is happening. If we discovered if you drop or strike them with a hammer and add some energy, it screws up the alignment of domains. I mean, that makes sense. If I all of a sudden smash this thing right here, maybe that one will point that way, this one will point that way, this one will point this way, this one will point that way, and all of a sudden, yeah, it's kind of been messed up a little bit, right? So that's one thing you can do. The other thing you can do is you can heat them. Again, electrons are notoriously hard to find. We'll talk about this more in the future, but heating causes everything to move more, which means your electrons move more. Well, if your electrons are moved more, it then screws up the alignment of them. And so we've actually discovered that all magnets all of a sudden cease to work at a certain temperature That's called the Curie temperature, probably named after Marie Curie. So if you heat a magnet up enough, it ceases to be magnetic. Mostly because all of the electrons that are going on inside here are vibrating so ridiculously fast that they're no longer aligned anymore. Of course they're not aligned, they're vibrating all over the place. So it's hard to talk about this stuff because I can't just draw you a picture of it because there's nothing to draw a picture of. You know what I'm saying there? And that's what makes physics both awesome and really annoying, because I can totally draw a picture of someone playing baseball and we can talk about forces and kinematics. I can't really draw you a picture of an electron. What does an electron look like? We really don't know. Right? So anyways. Okay, now here's what we do know. Obviously magnetic fields must exist then, right? Because we know that magnets operate in the exact same way as electrostatics, as gravity. So the symbol we've given to that is the letter B. Again, I don't know why they chose the letter B. Probably because M is already used for mass. So capital B is used for magnetic field strength. And we probably want to give a little arrow hat on top of it because we may want to know what direction it's traveling. We may or may not. So again, magnetic fields are considered strong, and the unit we have is named after Nikola Tesla. So capital T is the unit for magnetic field, T. I want to speak to that for a second. When I graduated high school, I graduated in 2002, just so you know how old I am now. The Tesla actually wasn't the common unit at the time. I learned about magnetic field strength as something called magnetic flux density, actually. That's what I remember learning about it at the time. And we probably used this unit right here when I learned it. It was called a Weber over a meter squared. And what scientists have discovered over time is that all of these units here are kind of equivalent to each other. Kilogram per current per second squared, Newton times second over Coulomb per meter. All of these things were equal to each other, and it was getting really annoying to have like 9 different ways of measuring a magnetic field. It was also getting annoying calling it a flux density or calling magnetic induction. And so fairly recently, it's been decided, let's just go with capital T for Tesla and keep it simple. But I need you to be aware that a Tesla is not a base unit. Do you guys know the base units in physics? Let me give you some. Kilogram is a base unit. Meter is a base unit. Second is a base unit. But a kilogram meter per second squared is known as a Newton. You guys know how there's some units that are like different ones, like say a Newton? Okay. This is a mass times by an acceleration. Mass times acceleration is force. Force is measured in newtons, but a Newton is actually like a newer unit type. Teslas work the same way. A Tesla is a conglomeration of like all sorts of other units. Fair enough? Magnets are really hard for us to have a frame of reference for as well, so I put a couple of things down on here for you to be aware of. The Earth's magnetic field is actually ridiculously small. It's actually 5 times 10 to the minus 5 Teslas. So it's actually barely noticeable, but it's enough that we can actually have a compass work. Believe it or not, fridge magnets and lab magnets are actually way stronger in terms of a field than the Earth itself. Kind of crazy. The surface of a star, by the way, is a massive magnet as well. So there's a lot of electromagnetic fields obviously coming off of the sun. Okay, let's talk about fields then for a little bit here. We need to know the conventions for field lines. In electrostatics, it was always based on a hypothetical positive charge. Well, the rules for magnetic field lines are always drawn towards the south and away from the north. That's the convention they went with. So if you ever have a magnet and you're trying to draw some field lines, draw them away from north and towards south. That's why. The reason why we do this is that this imitates the direction that a compass would point. Because really, a compass is just really a small little baby magnet, right? You guys know what I mean by a compass, right? We're going to use them tomorrow, where there's like the north, south, which way does it go? East, west. And then the compass is like a little needle that kind of points like this, right? And usually you color like one side of the needle and not the other side. Well, the little needle that you have, there's a north and a south end to that compass. We're actually going to discover tomorrow, this is a pain in the butt. Usually the ones I have, they color them half red and half white. And you would think that there should be some sort of rule that red is always south and white is always north. There isn't. And so I have a whole bunch of compasses where if you line them all up in the same direction, like let's say that this is north over here, I actually have compasses that sometimes the red end will point north and sometimes the white end will point north. That's like, why can't it just be consistent? From the same compass type, yeah. I know, you would think that they should have just painted them all the same, but you know, they weren't consistent, right? They just found something magnetic. They cut it out in a shape. They painted half white, half red, but they didn't actually bother to test which half was white or red. They just knew that one half was one half was the other. So you'll see it tomorrow. It's a pain in the butt. All right, anyways, moving on. The number of field lengths is how strong the field is. So if you have a lot of lines, it's a really strong field. If you have them really close together, right here, see how all these lines are really closely compacted? Right here is a really strong area of a field. Which, doesn't that make sense? Wouldn't this magnet right here be very powerful in that general vicinity? How powerful would you expect the magnet to be over there? Not as much. Yeah, there'd still be some magnetic interaction, but not as much. So, this is pretty obscure, but if a magnetic field line is curved, the direction of the field is tangent to the curve. If you don't know what that means, say you're looking at this point right here. Okay. See how this is on the side of a curved line right here? A tangent, if you've forgotten, is basically a line that just barely grazes the curved surface. And so we would say that right at this point right here, the magnetic field is actually pointing that way. At this point right here, if I were to draw a tangent, it's the line that just barely touches. I would say the magnetic field is going that way. So the magnetic field always kind of changes depending on where you are. Okay, so here's a good example of two magnets interacting. Here's a north-south magnet with a second north-south magnet. So I've drawn three field lines right here. I think it stands to reason that the strongest location that there will be a field will be between these two things. And by definition, we always draw a field from north to south. So three field lines right here matches. However, I could probably add a few more. It probably would curve around a little bit like this. I could probably have it curve a little further out like that. I could even suggest that maybe it's pointing in towards the south pole, because it always points towards the south pole. It always points away from a north pole. And I could even maybe argue that this is really looping back around to that south pole in a way. And so you can often have like quite crazy and intricate patterns of field lines. Okay, here's some pictures that kind of illustrate them. What happens when you start putting these things together? Here, there's a very intricate pattern where if I drew the field lines, it would be drawing away from north and towards the south. Here we got the same thing. This would be going away from north and towards the south. In between the U-shaped magnet, away from north and towards south. And then right here we got a bit of a problem. Do these two north magnets want to be near each other? No. You can actually see that there's kind of a bit of like a vacuum here in the middle where there's really not a lot of lines going on, because really this is trying to get away, 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 and you kind of have an absence of a field right here because you're really trying to oppose each other at that point. So anyways, it's likely that you'll be given some field diagrams and you have to interpret them. It's not overly hard, you just have to know a field always points south. There you go, that's all you got to know. A field points south. Okay, which then leads us to my last topic. The most common magnet that we'll actually discuss is actually the Earth, because the Earth actually behaves as a giant magnet. One of the reasons why is that internally the Earth is made out of iron. We have an iron core towards the middle of our Earth. Earth actually acts as a magnet. And like I started off our lesson with, this is allowed for orienteering, because now sailors or explorers can now try to find their way around if they know how to use a compass, right? However, you're going to hate this. This is going to change your life, and you're going to hate the stupidness of science. There's actually two different words I need you to know. First of all, there is a magnetic pole and a geographic pole. Earth actually has a geographic and magnetic pole, and I've got some pictures to help illustrate it. So I'm going to flip back and forth here. Here is where Earth's magnetic pole is. Here's where Earth's geographic north pole is. Okay. Geographic north is based on the fact that Earth spins. You guys know how Earth spins on its axis? That's what the geographic north pole is based on. Unfortunately, the north pole of Earth's internal magnet is not in the same spot. So even though Earth rotates on its axis, the magnet itself is slightly off. Now the good news is it hardly matters. The distance between these two locations right here is not all that much. And in most locations on Earth, I'm going to use a new color here. If we are right about here in southern Alberta, and you have your magnet point towards magnetic north, it's really pointing the same way as geographic north most of the time. Even if you're way over here, if your compass is pointing right here, it's more or less the same as geographic north. But this would be a really weird thing. Let's say that you were exploring the Arctic and you were standing right here. Your compass would point this way, but north is technically that way still, because north, as we define it based on our maps, is actually defined based on the geographic North Pole. So there's actually a few weird anomalies. Here's the second one. Earth's magnetic pole, as we've been tracking it, has been moving. I found this slide to help illustrate it. Earth's magnetic pole is somewhere up here, up in northern Canada, up in the Northwest Territories, up by, where is it? You can see it on here. There's Victoria Island. Anyways, Earth's magnetic pole has actually been moving slowly over time. Why? Well, why does Earth have a magnetic pole in the first place? Well, because internally, inside of the Earth, there's a core, there's that magma that moves around. It's not stationary. And so we actually recognize that Earth has actually had its North Pole, magnetic north, move over time. But the actual geographic North Pole is actually up here. Isn't that a pain in the butt? That one, they're not the same. And two, one of them is moving. Why is the geographic pole not moving though? Because that's what the Earth is spinning on. Does that make sense? If you can kind of imagine the basketball analogy, here's the Earth. The Earth is actually tilted. And then these poles right here, the Earth spins around on that. Okay? So the Earth will hopefully never deviate from spinning on that. Otherwise, who knows what that'll do to our ecosystems. But if these are the north and south poles right here, the axis of rotation, the magnetic pole is over here. Slightly different spot. Okay? Annoying, but we can live with that. However, there's one more problem. What is a compass supposed to do? A compass is defined as the field pointing towards south. When magnets were first used as compasses, imagine that there's a person right here, and the person is orientating their compass, that's a compass, and they know that this way is north. The needle of their compass pointed north, so they called that the north end of a compass needle. That was the worst decision they could make. Why? Yep. So let's say we want to call this north. That's awesome. Great. But you know what we can't do? We can't call that the north side of the needle, because do north things want to be near other north things? No. And this is why this was a really poor choice, is that they called this the north end of the needle because it points north. But if we're going to define this as the north end of the needle, it means that this is actually south. This is going to blow your mind. The North Pole is actually the South Pole. The North Pole is technically the South Pole, because we have defined a compass as the north needle, and the north end of a magnet technically points towards the south. And so many maps and pictures that you see, I've actually listed this here on the bottom of my slide here, many diagrams are actually backwards, because they don't account for that technical bit of science that normally we don't really care about. But yeah, let me show you some more pictures here. So here's a picture of the South Pole again. Now, we call this geographically south, but this slide right here, this called it the magnetic South Pole, but that's incorrect. This is not the magnetic South Pole. It's actually, oh, you can't even see that. Let me fix that. It's magnetic north. Yeah. Magnetically, this is actually north. It's geographically south because it's the bottom of the globe, bottom, right? And it's what the Earth spins on. But it's technically a North Pole because the south end of a compass points towards it. Okay. Here's another picture that kind of illustrates it. This is the best one. This is, well, actually, no, this one's still my wrong one. I have one more left. This says that it's magnetic north, but it's not. If you are standing right here and you have a compass, the compass says the north end of the needle is pointing that way. But norths don't point to norths. Norths point to souths. So we technically have a South Pole up where Santa lives. We've just gotten into the habit of calling it north. So frustrating. This last one here is no, still not that one. Here we go. This is the actual picture that is in physics. This is conceptually correct. There is a geographic North and South Pole. where we believe them to be. North, south, east, and west, geographically, we can't really change that. So we've defined this as being north, south, I guess this would be the east, this would be the west. And that convention is kind of stuck. We can't fix every map from north, south, east, and west. That's kind of stuck. We've based it on what the Earth rotates around. So the Earth is going around in circles based on the geographic north and south poles. Okay? Then when compasses were discovered, the first person with the compass says, oh, hey, look, this thing always points north. That better be the north end of the needle. Big mistake, because norths don't point north, norths point south. Now, since our compasses are now all kind of locked into place, it means that what they're actually pointing to then is south is actually up here magnetically, and north is actually down here magnetically. And they're not even in the same spot. Doesn't science suck sometimes that like we can't fix these problems? Do you guys get the why we can't fix them now? Now that like hundreds, if not thousands of years of science have been developed based on these theories, it's kind of like it's fractured. And so you always have to be very specific as to whether you're talking about magnetic or geographic north. And then you may have to have the conversation of, is it actually south in the north or north in the south? Because some people will still draw pictures like this one right here. Like this one's a good one. This one actually shows a proper picture. The south end of Earth's magnet is actually way up here in the North Pole. But you will still see pictures like this one right here that it called it magnetic north and it did it incorrectly. So anyways, did I make that clear? Because I think I'm repeating myself now. Frustrating. Yeah. You know what? You probably won't get assessed on something quite like that. However, they may. It's very likely if they talk about Earth's field that you're supposed to know that the south is actually up here. No. So just go with south as being what is up top here. Does that make sense? Yeah. It's frustrating because you have to like go through the whole conversation of what are you asking about, magnetic or geographic? Do you want the actual magnetic or what everyone thinks is magnetic? Okay. Okay, that's it. That's what I finished for my lesson here. Here's what I'd like you guys to do to end off class. Okay. On Moodle, I'm trying to experiment with other ways to, I don't know, 1, help you learn, 2, keep you accountable a little bit. I hate to say that, but a few of you sometimes fall behind. So here's what I've done. I've done 2 things I want you to work on. 1, if you click on the lesson for magnetism, I've put 5 practice questions at the end of it that are all about you understanding the theory behind this. I'd like you to try those. If you try those 5 questions, you get credit for doing the lesson. Okay. The other thing I want you to do is do the reflection, and please do this right away. Okay, don't wait 3 weeks and do a reflection, because I want to know how I can help you now. Here are the 4 main things I taught you today. Reflect on them and tell me what you understood about it. So quick recap, then I'll give you time to work. 1, do you feel like you're confident and that you understand the similarities and differences between magnetic, electric, and gravity? Okay, we spent a lot of time talking about that. Do you feel like you understand the conventions about magnetic fields? Magnetic fields point south. Magnetic fields point south, which we actually thought was north, which was dumb. Okay. Do you understand the difference between geographically magnetic poles? Geographic and magnetic poles. And do you understand this north and south problem, where north is actually south and south is actually north, and this is ridiculously stupid. So anyways, if you could, can you guys work on those 5 questions and write a reflection? And that's all I've got. So that's kind of the end of the day. Tomorrow we're going to do a lab where we actually play around with some magnets. I'll probably let you guys do stations, and you'll kind of get a chance to explore working with magnets for a bit. And then on Thursday, we're going to do a lesson on moving charges and magnetism. And then Friday, we'll do some practice questions. So that's our week. Tomorrow, a lab. Thursday, another lesson. And then Friday, some practice questions. So, sound good? Okay, I'll just stop this and then I'll come help.